Okay, I think we are live. I hope you guys had a good break. I got a new camera, so we're able to start back things in the classroom again. And today we'll go over chapter 2.2, which is tangent lines and mean value theorem. So the main focus that we'll have on this lesson is trying to find the equation of the tangent line. Now, through derivatives, you've become quite familiar with finding the slope of a tangent line at a certain point, and today we'll extend that into the actual equation of a tangent line and how to find them in various scenarios. So let's get started. If you look at your notes package, you'll see that the first 3 points are three different scenarios where you can find the equation of the tangent line. So we'll start with that. So there are three possible scenarios that you'll be given and asked to find the equation of a specific tangent line. Number one is the point of tangency is given to you. Now, this is the easiest case, right? If you have a curve that looks like this, and you are given a point t comma, let's say f of t, that your line has to be tangent to, right? Okay, the first step, obviously, is to calculate the slope of the tangent line, which is f prime of t, right? And then you would simply use the slope point formula that you're quite familiar with from Math 10, right? So you have a slope of f prime of t, and that line has to pass through t comma f of t. So we'll go x minus t plus f of t. And that's it, right? So now you have your nice equation of the tangent line, and that's it. So that's the most simplest case. The second case is that you have the problem or something else gives you the slope of the tangent line, but not the point of tangency, okay? So slope m is given. Okay, now we have to, think a little bit more. The defining point, the most important point of a tangent line, if you think about it, right, is actually the point where it's tangent to the curve. That single point gives us all the information that we need. So even though the problem may not give us the tangent point, when we're trying to find the equation of tangent lines, we should always start with the point of tangency. So once again, the first step here is to set up the tangent point. So use a variable. I like to use the variable t, so I'll first set up t comma f of t. Okay, and then number two, I'm going to find f prime of t. But now I'm given the slope of m, so I can set the equation f prime of t equals m, and I can solve for t. Whatever number of solutions that I get, then I can set up the tangent line using the point slope form. So let's say that in this scenario, I solved the equation and got this tangent line. But note that if you have a complicated curve, you might have multiple solutions to the equation f prime of t equals m, since visually, as you can see, there's another point here where the slope of the tangent line looks pretty parallel to the original one. So we'll learn about this more in depth later, but this is the shape of a cubic function, and in a cubic function, there may be 2 points where the derivative will equal each other. So watch out for multiple solutions. All right, so the final case is the most tricky one when you're given an external point. Now, the problem will tell you, hey, I have a curve right over here, and I need you to find the slope of the tangent line that passes through an external point. Let's call it a comma b, that is given to you by the problem. Now, as with the previous two scenarios, the most important part of the tangent line is the point of tangency. So once again, we'll set up the tangent point first. seems kind of counterintuitive, right? The problem gives you a comma b, but first we'll set up t comma f of t. So the tangent line will look sort of like this. So we'll set up, hey, I'm going to set this variable. And then number two, what we're going to do is we're going to artificially set up the entire equation of the tangent line based on t. So set up equation of the line based on t. So we would literally set up this, but everything will be in terms of x and t, right? The reason that we do this is that once we set this up, now we have an equation that represents every single possible tangent line that this curve could have. And then our final step is set that equal to a comma b, or rather plug in a comma b. And solve for t. And once you have solved for t, you can plug t back into the original equation and get that specific tangent line that goes through a comma b. Now, that's one way to do it. Another way to do it is to realize the fact that you can use the average rate of change from a comma b to t comma f of t. And then you can set that average rate of change equal to the derivative at x equals t, right? So that's kind of like, that's almost the same thing as plugging in a comma b, but that's more like average rate of change between these 2 points is equal to the derivative instead of directly plugging in the point. Those two equations have the same effect, and you will have both method written into your notes package. So right next to your note package, I would draw out these 3 scenarios. And remember, the most important point of any tangent line is going to be the point tangent to the curve. Okay, so let's get some practice in. All right, let's see what I can do here. I'll erase the board and we'll start with the practice questions. Okay, so your workbook, we're doing chapter 2.2. Okay, so number 1, the graphs of f of x and y equals x plus 1 are tangent at 2 comma 3. Find limit h goes to 0 of f of 2 plus h minus f of 2 minus h over h. Now, we studied these forms of limits a lot in the previous unit, and by now you should be quite comfortable with realizing that this is twice the derivative at 2, right? Because this is plus h and minus h, their difference should be 2h, so you put a 2 down and then you multiply a 2 at the end. Now, f prime of 2, it literally says that the curve is tangent to the line x plus 1, right? So x plus 1 has a slope of 1, which means that we can directly plug that in to f prime of 2, and we get the answer of 2. All right, so that's pretty easy enough. Just understand the situation and evaluate the limit. Number 2, the slope of the tangent line drawn from a comma b, a point on the graph, we have f of x equals x squared minus 5x plus 3. Okay, the slope of the tangent line drawn from a comma b, which is a point on this curve, is 3. So the slope of the tangent line you can find from f prime of x. So our first step would be to differentiate the function. That would be 2x minus 5, and we need to set that equal to 3. So 2x equals 8, x equals 4, and your point is we have 4 comma, and we need to plug this back into the original function. So that's 16 minus 20 plus 3, which should be negative 1. So we have a equals 4 and b equals negative 1. So a plus b should be 3, and that would be your answer. Again, pretty simple problems at the beginning. Okay, I'll go through number 3 with you, and then number 4 is a slightly different kind of challenge, so I'll actually leave that one for homework. So let's go through number 3. Okay. The equation of the tangent line drawn from 1, 3, which is a point on the curve, we have y equals x cubed plus 6x squared minus 11x plus 7, and that is mx plus n. So we're finding the tangent line from 1, 3. Again, the first thing we need to do is figure out the derivative. So we go y prime equals 3x squared plus 12x minus 11. And we can plug in 1. So that's 3 plus 12 minus 11, which is 4. So now we got our slope, and we got our slope and the tangent point. So we can figure out the equation right away. 4 times x minus 1 plus 3, which equals 4x minus 1. And find the value of m minus n, so that's 4 minus negative 1 would be 5. All right, so I'll assign 4 for homework. 4 requires a little bit of not really calculus knowledge, but how well can you manipulate the polynomial expression. It's quite an interesting one, so please try it out. Number 5. All right, let's do number 5. Okay, polynomial function f of x satisfies, and we got a limit expression. So notice how everything that we've been doing in previous units sort of accumulates over time. So make sure to go back and review the ideas and basic concepts that we had in the derivatives and limits unit. So this equals 4. Let the equation of the tangent line to the curve f of x at the point where x equals 2 be ax plus b. So we're trying to find the tangent line at x equals 2. Okay, so now let's take a look at the limit. Plug it in. Denominator goes to 0, but the limit exists. Therefore, the numerator goes to 0. So f of 2 must be 1. And if we just replace this with minus f of 2, we can see that this becomes a derivative expression. So we have f prime of 2 equals 4. And there we go. We got the slope. We got our point 2, 1. So we can immediately write down the equation. 4x minus 2 plus 1 equals 4x minus 7. And a times b would be negative 28. Right, so as you can see, most of the problems follow a similar pattern. There are just different ways that you have to obtain the slope of the tangent line, so y prime or f prime, and then what the tangent point is. Okay, number 6 asks us for a slightly different type of line. Let the equation of the line passing 1, 2, a point on the curve y equals x cubed minus 3x squared plus 4, while being perpendicular to the tangent line. Okay, so this is a concept called the normal line. You might have heard of normal force in physics. So a normal line, normal means perpendicular, right? Perpendicular. So a normal line would be, if you have a curve and you have the tangent line here, a normal line would simply be the line that is perpendicular to the tangent line while still going through the tangent point. So remember that the slopes, the product of the slopes of two perpendicular lines equals negative 1. So what we need to do is simply find the derivative to find the slope of the tangent line, take its negative reciprocal because the product is negative 1, and then simply use the point slope form again, right? So that's, I think, pretty easy to do. Y prime equals 3x squared minus 6x, and we are at point 1, 2, so y prime of 1 would be negative 3, And there we go. So your slope of the normal line would be the inverse reciprocal of this, right? So it would be positive 1/3, so that they multiply out to be negative 1. So your slope is 1/3, and your tangent point is 1, 2. So your line would be y equals 1/3 x minus 1 plus 2. And it says to find b minus a, so we'll expand that, 1/3 x. That's 6 minus 1, so that's 5/3, I think. So that would be negative 5/3 minus 1/3, so that would be negative 2 would be your answer for this one. Okay, so now we've done normal lines, tangent lines. And number 7, what is the area of the region by the, So we'll be talking about area under curves in our integration unit, but number 7 asks you about the area between the tangent line, the x-axis, and the y-axis. So as long as you get the tangent line and its xy intercepts, you should be able to figure the area out. So I'll leave that to you for homework. Number 8, the tangent line 1, 4 on the curve intersects the curve again at a, b. So that's just a matter of algebra, right? If you haven't done synthetic division, then this will be sort of a challenge for you. So you might want to skip this one. Synthetic division is when you want to solve polynomial equations of degrees 3 or higher, right? So the quadratic formula exists for you to solve quadratic equations, but above degree 2, technically there is a formula for cubic and quartic equations, but they're so long that nobody memorizes it. We use a method called synthetic division, which I'll explain when we actually solve this problem in the next lesson. So if you don't know how to solve those cubic equations yet, you can skip this, but otherwise, you can attempt number 8 for homework. Let's see. Number 10. Should we try number 10? Okay, number 10 says, the graphs of line mx plus 2 and the curve negative x cubed plus 2x intersect at 2 different points. Okay, find m. Let's see if we can work this out without a graph. We might have to also use synthetic division for this. Okay, you know what? I'll do number 8 right now, and then number 10 you can do for homework, because, okay, let's do number 8. Okay, the tangent line on the curve y equals x cubed minus 6x squared plus 12x minus 3 intersect the curve again at another point. Okay, so let's find the tangent line at 1, 4 first. So we can say y prime equals 3x squared minus 12x plus 12, and that has, we can plug in x equals 1. So 3 plus 12 minus 12 equals 3. So we can say that the equation is y equals 3 times x minus 1 plus 4, which equals 3x plus 1. Okay, so we got 3x plus 1. And then we need to find the intersection of these two graphs again. So if we write down the cubic equation, we need x cubed plus, minus 6x squared. And then we set them equal, so it's plus 9x minus 4 equals 0, and we need to solve this. Okay, so if you don't know synthetic division, here's how to solve these cubic equations. Make sure you have the orders of the terms in descending order, and then you're going to write out the coefficients for each ordered term all the way up to the constant term. So I'm going to write 1, -6, 9, and -4. And if there is a power that's not, if there's an equation where the power is missing, then you write 0 in place of it. The goal is to get every power, the coefficient of every power in descending order. Now, synthetic division is based on polynomial long division. So it's a quicker way to deal with just the coefficients and not the x terms. Now, what we want to do is we want to find a particular number. That particular number will essentially be a number that divides this polynomial, and you'll see what I mean. So we look at the constant term, and then we can see, we can try any number that's a factor of the constant term, okay? So -4 has the factors 1, 2, and 4, and also -1, -2, and -4. The reason that we're doing this is that when we're trying to divide a large polynomial, so here's a large polynomial, LP, and then we want to split it up into, our goal is to split it up into monic terms, right? So we have x minus a, x minus b, x minus c, and so on. And what we're trying to do is we're trying to find these individual numbers, a, b, and c. So how that happens is if we plug in a, then this entire product, right? Because it's in factored form, right? So if we plug in any of these roots, the whole larger polynomial should go to 0, right? So we're trying to find these numbers. And the reason that I tell you to find, try the factors of the constant term is that when you multiply out all the roots in the equation, they will eventually all multiply out to the constant term. And one of the numbers that we can immediately check for is actually 1. As you can see, if you plug in 1, if you take the sum of all the coefficients, right? If you plug 1 into a polynomial, that means you're summing up all the coefficients in that polynomial. If you look at the coefficients here, you'll see 1, -6, 9, and -4. So that's 10, and that's -10, and that will go to 0, right? So that means that x minus 1 would be a factor of this polynomial. So now, since we found that number 1 that makes the thing 0, we can put our number here on the left side, okay? And now we follow this pattern. So for the leftmost coefficient, we can put it straight down, and this goes to 1, like that. And then we're going to take this number on the left and our number that we put down, we're going to multiply it, and we're going to send it over to the next position. So 1 times 1 is 1, and we'll write down our new multiplied number here. The next thing that we're going to do is we're going to vertically add it. So -6 plus 1 equals -5, and write it down like that. The next step is to take the leftmost number that we picked and then multiply it and put it over in the next position, so -5. And then we keep repeating this pattern. We add vertically, so that's 4, and then we multiply it and put it in the next space. Well, we multiply 1 with 4, and then 4, and then when we add it, the final number, I'm going to box it out because that's what the remainder is going to be 0. You have to have 0 at the final number in order to have success factoring the polynomial, right? That means that our total value that we have for the remainder is 0. If you got something other than 0, then you need to try this process again with a new number that would be an integer factor of the constant. Okay, so now we'll interpret the results. So right now it's saying that, hey, this can be divided by 1, and that means that the factor is x minus 1, right? So if you try 1, that means that your actual factor would be x minus 1. And then your coefficients that you've laid out here will be your quotient. That means that when we divide a cubic by a monic term, we get a quotient of degree 2, right? So this will be the x squared term. So that would be 1 times x squared. This would be -5 times x, and that would be plus 4 as the constant term. And then the 0 here means that the remainder is 0, so we don't need to care about that. Okay, so now you can try this again, or because it's a, it's a quadratic, we can immediately factor this again. So this goes 1 and 4, and both are negative. So we get x minus 1, x minus 4 for our quadratic here. So that would mean that there's another x minus 1 factor and x minus 4. And there you go. We have factored this cubic polynomial into these monic terms. So that's where synthetic division would be useful. So this process is called synthetic division. It replicates the process of long division, right? So if I did a long division in the traditional sense, and then I would have to write x minus 1 here. I would have to go, hey, x squared, that means x cubed minus x squared, and then I have to subtract it. That means that this would go to negative 5x squared plus 9x minus 4. And as you can see here, that's how the simplified process works, right? I multiply this with that, so that's why I'm multiplying this with that to get 1. And then once I subtract these, that's the equivalent of adding this with that, because this is x minus 1, but we wrote positive 1. We wrote whatever number that makes this expression 0. So that's why in the end we need to flip the sign here. So that means adding here is equivalent to subtracting negative 1 from negative 6. So instead of going through all that long process in long division, we can simplify the entire numerical process by using synthetic division. And the next multiplication goes the same, right? We need a negative 5x in order for this term to multiply with that term to be negative 5x squared minus 5x, and then this would go away. And adding 9 and negative 5 is the equivalent to, so this is plus 5, right? It's the equivalent to subtracting 5 from 9, and the process goes on, right? So this is a much more efficient way of trying to factor a polynomial of degree 3 or higher. Okay, so we've gone through all of that. And it's time to solve the equation. So this equals 0, right? So since we were initially trying to find the intersection of this guy and this guy. So we have the solutions x equals 1. So that would be considered a double root, a multiplicity of 2, or x equals 4. And since it says that it has to intersect at another point than our original point, then we can cross this out. So therefore, x equals 4, and our desired point would be 4, comma, and we have to plug this guy back into the top equation. That would be 4 times 4 times 4 is 64 minus, so that's 64 minus 16 times 6, that's 96, plus 48 minus 3. So 64 plus 48 is 112 minus 96 is 16, and that would be 13. 4 comma 13 would be your final answer. So find b minus a, so that would be 9. All right. So as you progress onto like pre-calculus 12 and calculus 12 APIB, you'll be expected to quite quickly solve these cubic or maybe even quartic equations. So practicing synthetic division to factor polynomials would be a great skill to have in your future senior math courses. Okay, I would encourage you to look at number 10 a little bit more. If you're stuck, you might want to go on Desmos and try to see what the curve looks like. But I feel like there might be an algebraic way using synthetic division to figure out the scenario here. So we'll figure that out next class. Number 11 is also a challenge. Is there a similar question? No. Okay, so number 11, I also would encourage you to do for homework. Now we're actually, really starting to ramp up our difficulty a little bit. Out of all tangent lines to the curve, which is given below, the line with the maximum slope, right? So you're trying to find the maximum slope of the tangent line, which means you have to find the point the derivative reaches a maximum. So I'll encourage you to work on that. Oh, we skipped number 9. Okay. All right, so we'll tackle number 9 since that's the type of problem where our slope is given but not the point, and it might have multiple solutions. So let's see what those types of problems look like. There are 2 different lines, so it gives you that warning. There are 2 different lines tangent to the curve y equals x cubed minus 3x plus 1 that have a slope of 9. So your slope of the tangent line is 9. What is the distance between the 2 points where the tangency occurs? So that means that it intentionally tells us to focus on the tangent points, which we already are going to do. Okay, so I'm going to let the tangent point be t comma f of t for our variable t. Okay, so here y prime is going to be 3x squared minus 3. So we're going to plug in t, so 3t squared minus 3, and it says it has to equal 9. So if we go here and cross these out, and then t squared equals 4, t equals plus minus 2. Okay, so we got 2 points. We got plus minus 2. So it has to be 2 comma f of 2, which is 8 minus 6 plus 1, which is 2 comma 3, and negative 2 comma negative 8 plus 6, so that's minus 2 plus 1 equals negative 1. And these two are our points of tangency. What is the distance between them? We can simply use the distance formula, right? Square root of 2 minus minus 2 is 4. So that's 4 squared plus 3 minus minus 1 is, again, 4. So 4 squared plus 4 squared, which is equal to 32, which is 4 square root of 2. So that would be your answer for number 9. So it's pretty easy enough once you set up the derivative and find those tangent points. Okay, so we've done number 9. Number 12. What is the minimum distance between the curve y equals x squared and the line y equals 2x minus 3? Ooh, okay. So this is a little bit of an interesting one because you could start bashing algebra and you would get to the answer if you did that, no problem. But maybe it's worthwhile to sort of sit back and wonder if there's a better way to do this. Okay, so we have the curve y equals x squared, and that looks like this, and the line 2x minus 3. So that's at 1 comma 1, what does that give you? It gives you 1 comma negative 1. Okay, so it's 1 comma negative 1, and it has a y-intercept of negative 3. So it will look like this line right over here. Okay. So these two lines won't be touching each other. To make sure of that, you would need to go for the discriminant. But we can compare the function value at 1 comma 1 and see that this line passes 1 comma negative 1, which means that the quadratic will grow faster than this line could keep up, so it won't have any intersections. When we're solving these types of problems, it's kind of, I'd say it's kind of important to keep track of, if possible, where the graphs are and sort of visualize the situation. Imagine, if you remember the Unit 1 exam in the final problem, it was very helpful to visualize that complicated absolute value graph to see what types of translations could be made. All right. So the minimum distance. So here we have to think about this a little bit geometrically. I don't know if you guys know this formula, but if we have a point like a comma b and a line that's in standard form, so like that's mx plus ny plus l equals 0. then there's actually a formula to compute the geometric distance. So that's the length of this particular segment. So that's going to be m squared plus n squared. Absolute value, you just plug the expression into the standard form. So am plus bn plus l, absolute value closed, and this would actually give you the distance of the tangent, distance between the point and the line. Maybe we don't want to go this direction for this particular problem. If we think about things a little bit more geometrically. Now, the distance between the line and a point on a curve, right? How can we figure out the minimum possible distance? What makes that criteria possible? Well, if I imagine a set of all the possible points that are exactly like one away from this line, then I would have, technically, I would also have a set of points over here, but we're really not caring about this part of the graph, so I'll only focus on the upper part. So the dotted line that I just drew is going to be the line of all points that are equally distant. So maybe I'm just going to assume that this is 1 for the demonstration. But this line is going to be the set of all points that are 1 away from our given line, 2x minus 3. So if we increase that distance, it's going to stay parallel. The dotted line is going to stay parallel to 2x minus 3, but it might go up and down, right? So the moment that the dotted line is tangent to our parabola, say here, this point on the parabola is going to be at the minimum possible distance away from our original line, right? Because if the line goes any lower than that, if the distance gets any shorter than that, then there won't be any points on the parabola to satisfy that distance. So the moment when, so this has a slope of 2, right? The moment when we have a tangent line of slope 2 on the parabola, then that tangent point is going to be the point where the distance between this line is going to be minimized. Okay, so this kind of logic operates a lot, actually. So for a line, if I have the set of all points that's equally distant, it's going to be a pair of parallel lines, right? So let's say A, then this line is going to have a distance of A, and the bottom line would also have a distance of A. If I have a point of the set of all points that are equally distant from a single point, then we learned by definition that would give you a circle, right? Sort of like that. So using these geometric properties may be beneficial to you when solving these seemingly, very algebra-focused problems, okay? Since now, instead of using that complicated square root and absolute value formula that we don't know how to take the derivative of, we can simply use the fact that whatever tangent line with slope 2 we have on the parabola, that tangent point is going to be the point that minimizes the distance. Okay, so now let's actually compute that. Let's call this point t comma f of t. Well, we know that it's x squared, so let's call it t comma t squared. Okay, so the derivative of y, so if y equals x squared, then the derivative y prime equals 2x, and we plug in t, 2t must equal, well, 2, since that's parallel to 2x minus 3, so t has to equal 1. So this will be 1 comma 1, and we can now simply calculate this distance between 1 comma 1 and line 2x minus 3. Okay, so I'll write down that formula for you again, since this is now a much more manageable situation. We actually know what point to plug in. The distance between a line and a point. Okay, so let's call this point x1 comma y1, and let's call the line in standard form ax plus by plus c equals 0. Now, the way that you actually prove this is that, hey, it's going to be perpendicular to this line. So you would actually find the line that is perpendicular to the original line, so ax plus by plus c equals 0, and then you would find the intersection of the original line you have and the perpendicular line you have. I won't go over the proof now, but if you're interested, you can ask, or maybe I'll upload a proof of that in the Google Classroom, okay? So originally you would find the perpendicular line that goes through the point and then find the intersection, but this distance d is going to be, first of all, you take the square root of a squared and b squared. So that would be the coefficients of your line in standard form. And then in the numerator, simply take the absolute value of plugging in x1 and y1 into this standard form equation. ax1 plus by1 plus c. Okay, so now let's apply that to this line. So this is equal to y, and if we put it in standard form, 2x minus y minus 3 equals 0. So we need to find the distance between 1 comma 1 and this point. So we're going to go square root of 2 squared plus 1 squared. Well, that's negative 1 squared, technically. Like that, and then in the numerator, we're simply going to plug in 1 comma 1. So 2 minus 1 minus 3, right? So that's minus 2. And then that would be our distance, square root of 5 under 2. And rationalizing, that would be 2 square root of 5 over 5. And that would be the answer to number 12. So this is a very helpful formula. The distance between a point and a line. I think the actual proof, the actual way to do it without like the algebra getting too messy is you actually define another point. You define this point, x2 comma y2, and then you do a system of equations. You do x2 comma y2 is part of this line, so you get one equation, and then you can say that the average rate of change between these 2 points is perpendicular, so that's the negative reciprocal of the average rate of change, the slope, I mean, of this original line. So you set up another sort of like a proxy point, and then once you put those equations together, you'll get a not so bad way of deriving this. Maybe I'll post it on Classroom in a couple of days if you're interested. All right, do we have more? Let's see. The equation of tangent line drawn to curve x cubed minus 6x plus 1 from point 0, 3 equals, okay, so number 13 is a classic example of the third scenario where you're given a point outside of the curve and you're expected to find the tangent line. Okay, so let's take a look at how you would solve that. Okay, so we have 0, 3, and we're drawing the tangent line from that point. So we're starting at that point and drawing the tangent line, but always we need to focus on the point of tangency. So we're going to set that point as t comma f of t. Okay, now we're going to take the derivative. Y prime equals 3x squared minus 6, right? So now we got y prime and we got t. So the next step we're going to do is we're going to set up the entire equation about x and t. So the equation of the line, I'm just going to call it L, is going to be y equals 3t squared minus 6, right? Since that's the derivative at x equals t, times x minus t, and then plus f of t, which is going to be t cubed minus 6t, so we're going back to the original function, plus 1. So this equation represents all the possible tangent lines that we could have. And the final step is to plug in 0, 3 into this equation. So 3 equals 3t squared minus 6 minus t plus t cubed minus 6t plus 1. And let's see here. That's going to be negative 3t cubed plus 6t plus t cubed minus 6t plus 1. Okay, so I think we're getting another cubic equation here. Let's move everything over to that side so we get a positive leading coefficient. So we'll get 2t cubed, and then 6t minus 6t will cancel out. Oh, this might be nice, actually. So 2t cubed equals, let's move the 3 over here, negative 2. Okay, so this is a very nice one. Okay, so t cubed equals negative 1, and the only possible solution is t equals negative 1. And the final step is to plug this back in here and get our equation of the tangent line. Y equals, so we got 3 minus 6 minus 6 x minus 1, so that's plus 1. And then we got minus 1 plus 6 plus 1, so that's 7 minus 1, that's plus 6. Did I get that? Yeah, okay, I got that. Okay, negative 3x plus 3 would be your equation, and a times b would be negative 9 as your final answer. Okay, so yeah, so that's how you would solve a typical drawn from the a tangent line passing through an external point problem. It's not that bad, but usually teachers will give you a nice scenario like all these terms canceling out, okay? Because the algebra could get pretty heavy. Number 14. Okay, so I'm going to leave number 14 up for homework, but I'll explain the concept, okay? Because it might be kind of confusing. So number 14 is a situation where there are two curves that are tangent to each other. So what does that even mean? Okay, so you probably will be able to visualize two curves being tangent to each other. So two tangent curves. Okay, two curves tangent to each other. Okay, so let's have a curve like this and another curve like that. Okay, maybe that's not the best drawing, but okay, like that. All right, so what does it mean when these curves are tangent to each other? The definition is that they share the same tangent line at that specific tangent point. So if I draw this green line, that means at the point of tangency, so that's one point that they meet. That one point that they meet, they have equal derivatives. And that means that those two curves will just touch each other and move off in different directions. That means that they are tangent to each other. So let this point be, let's call this alpha, comma, let's call this f of x and this curve g of x, alpha, comma, beta. Okay, so the tangent point is alpha, comma, beta. There has to be two conditions for this to be possible, right? So number one is going to be f of alpha has to equal g of alpha, obviously, and that has to equal beta, right? They must meet at one point. So their baseline condition is the function values have to be equal at that specific x point, x value. Number two is the important part, which means that the derivative at x equals alpha for f and the derivative at x equals alpha for g has to equal each other. So if their function values equal each other and their derivatives equal each other, then we can define the two curves to be tangent at x equals alpha. So you just need two equations, and number 14 has two variables, so you'll be quite fine for number 14. Number 15 is also that sort of scenario. The tangent line at point negative 1 comma 3 on the curve 2x squared plus 1 is also tangent to the curve that. So that requires a little bit, more of thinking that. So number 15 is like, hey, I have this curve that's tangent to one thing, like that, but it's also tangent to another curve, like right over here. So how am I going to figure that out? I'll leave the thinking up to you. You should try to utilize the logic that we've been using. Remember, the most important points that we have to be looking at are the points of tangency. Okay, so for the final, all right, so Rolle's theorem and the mean value theorem, I think I'll leave it out for next class, which will be on Monday, okay? So I said at the beginning of the course, there are a couple important theorems to memorize in calculus. We've already learned the intermediate value theorem and the Rolle's theorem and the mean value theorem and Rolle's theorem are going to be two important theorems to learn when we're considering derivatives. So we'll cover that in the next lesson. All right, so your homework for the next lesson is, so it's 2-2. I'll write it over here. That's going to be number 4, number 7, number 10 and 11, number 14 and 15. Okay, I hope you had a great start to your school year and we're progressing through well. So I'll see you guys next time for the continuation of chapter 2-2. All right, goodbye.